So we'll get partway through this lesson, and then we'll finish it off on Tuesday. We're going to be starting to look at a different type of motion. And we're going to start off with a thought puzzle. And you know what? We're going to vote. Is it possible for an object to have a constant speed, but also be accelerating? That's our question. Don't blurt out your answer. We're just going to think about it. Is it possible for an object to have a constant speed, but also be accelerating? Who says, Mr. Dewick? Yes, that's totally possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Owen, was that a vote yes, or were you just moving hair number 93 back? Because you did this as I was going by. It was kind of a decade. No, I think I said 13. Who says no? 1, 2, 3, 4, 5, 6. So, Taryn, if you were a good student, sadly, you might have been clever enough to look at the next paragraph and see that it says, for an object moving at a constant speed in a circle, its velocity is changing because its direction is changing. And if its velocity is changing, the object must be accelerating. It is possible to be going at a constant speed. And the reason is acceleration is a vector. It has both magnitude and if you're going around a corner, even if your speedometer magnitude isn't changing, is your direction changing? You're accelerating. There has to be an unbalanced force. Okay? If direction is changing, we're also accelerating. And Zach, that's going to be the weird thing that we're going to be talking about this unit. We're going to have a constant speed, but an acceleration. And the acceleration and the force are going to be causing a change in direction. Not a speed up, slow down, but a going around a corner or going in a circle. And because of that, we're going to have to break some habits that I've really drilled into you. And so one of the phrases you're going to hear me say, kind of the trigger for this unit, I'll always start out by asking, hey, what path are we tracing out? A circle, and we're going to move our whole mindset into what we're going to learn about moving in a circle. We're going to say, okay, not going to be staying in my winner minus loser Newton version. We're still going to use winner minus loser. We're going to have to tweak it. What we're going to look at is what's called uniform circular motion, which means if you're going around the corner page, your speedometer isn't changing. You're not speeding up or slowing down. You're accelerating, but by changing the direction, not the magnitude. We will look at a couple of situations, actually, where you're also changing the magnitude, but we'll only be able to analyze those, Braden, in a couple of specific areas. But they're cool applications, so we will look at those. If an object is moving in a circle page, it's accelerating because its direction is changing. So if its direction is changing, its velocity is changing, and since acceleration is a change in velocity, boom, boom. Okay. Now, some concepts here. If you're moving in a circle, like in this picture, your velocity is what we call tangent to the radius. It's at right angles to the radius. VC, I'll use a C for circular, is tangent to the radius. Tangent is another word for perpendicular. There's at least 3 ways to say perpendicular. Normal means at right angles. Perpendicular means at right angles. And at tangent means at right angles. Those of you in calculus, you've been looking at tangent lines. And that's the reason we use tangent here, is it's actually tracing out a tangent line right at the moment where it's contacting the circumference of the circle. This is important because a lot of people think when you're moving in a circle, a lot of people think that your velocity is in that direction. They think, for example, how many of you have been on a playground merry-go-round before where you're spinning really, really fast? And if you stand on the edge, you might think if you let go, you would go flying straight backwards away from the center along the radius. You won't. You'll end up moving tangent to the radius. When you hit the ground, you'll find you're running sideways to the circle, not straight back away from the circle. What's the direction of the acceleration? Well, there's 2 ways we can get the direction. The first is Your body, I've taught you, is a backwards accelerometer. When you hit the gas, you feel like you're getting pushed backwards. When you hit the brakes, you feel like you're getting pushed forwards. On the elevator, when it shoots you up, you feel like you're getting pressed down. When it shoots you down, you feel like you're about to fly up. So if you've been at Playland on, for example, the Music Express, where it goes in a circle really, really fast, what direction do you feel like you're getting pushed? Out. So which way are you accelerating? Yes. That's the key concept in this unit. If you're moving in a circle, which way are you accelerating? Toward the center. That we'll use that phrase because it may be more complicated than which way is it? Toward the center. If you're moving in a circle, Zach, which way are you accelerating? Toward the. If you're moving in a circle, Kevin, which way are you accelerating? Toward the. If you're moving in a circle, Karen, which way are you accelerating? Toward the. So, you ready? Which way are you accelerating if you're moving in a circle, Nick? Toward the. Which way is the net force pointing? Toward the. Who's winning? Toward the. In my winner minus loser equation, which way will the winning arrow always be pointing? Toward the. There. Your test is tomorrow. I could almost say you can now handle everything. Except, oh, wait a minute. There's a different way to calculate circular acceleration. So first of all, that's the experiential proof. You know you're accelerating towards the center because your body is a backwards accelerometer. Let's do a vector proof. To find the direction of the acceleration, we can do a vector subtraction. I can take VF equals VI plus AT and get the A by itself, VF minus VI over delta T. Now, delta T is a scalar. That's not going to change the direction. The direction of the acceleration is going to be the same as the direction of VF minus VI. How do I add two vectors together? Draw them. How do I subtract two vectors? I don't. What do I do instead? Okay, so I've got kind of a zoomed in picture on the next page. Here's VI, and then like a tenth of a second later, here's VF. I would like to subtract these two vectors. But again, I don't want to go VF minus VI. I want to go VF plus the opposite of VI. Okay. Looking at this picture then, VF is in that direction. VI is up and right. Sorry, up and left. So what's the opposite of VI? Down and? So there's VF. There's VI. And can you see if I draw the resultant, which way is it pointing? Toward the. So there's a vector proof as well. Okay? If you're accelerating in a circle, please trust me, you're accelerating towards the center. The net force is towards the center. Who's winning? Towards the center. When you're doing your free body diagram, which way will the winning force be pointing? Toward the. Okay. So an object that is moving in a circle is accelerating towards the center, or more basically accelerating inwards. I'll almost always say towards the center because it just reinforces to myself that it's a circle, and sometimes that center is important for other things as well. Example 3, suppose we have a ball on a frictionless tabletop. This is a top view. We're looking down from the ceiling, and we've got a circular track. So the ball is rolling along really, really fast. When it gets to here and leaves the circular track, what path will it trace out? Here's your options. Path A, due to the fact that the ball has some circular momentum, so it'll keep going in a straight path. In a circular path for a while after it leaves the track. Path B, because when there's no force from the track, the object will keep going in a straight line. Or path C, because when the track is no longer applying a force on the ball will fly outwards. Ooh. You know what, Paige? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So we're looking down from the ceiling. The ball is rolling, rolling, rolling. When it gets to here, which path will it trace out? Who says, Mr. Dewick, obviously it's path A. It's moving in a circle. It's going to keep moving in a circle. A. No one. Wow. Duh. It's B. Duh. It's B. 1, 2, 3, 4, 5, 6, 7, 8. Everyone. So C I've never been more proud of you. B is correct. Why? When it leaves here, what forces are acting on it? Well, I guess gravity, and that would be into the page because we're looking down at normal force. They're canceling out. Are there any unbalanced forces acting on it right here? So which way must it travel at a steady speed? I'm impressed because a lot of years some kids will pick C because they're remembering their merry-go-round experience and they think, well, there's something pulling me out. There is no force pulling you out. There's nothing that's going to make you suddenly start curving away. It's your imagination. I'm going to convince you of that. So, circle B. So here's the question then, Braden. Why is the acceleration inwards when clearly I feel like I'm getting pushed outwards? Isn't there a force pushing me outwards? Shouldn't I be accelerating outwards? I mean, clearly there's a force pushing me outwards. There isn't. I'd like you to imagine you're sitting in a car and the car is going really fast in this direction. That means your body wants to keep going in that direction. That's Newton's first. Your body wants to keep going in this direction. The road applies a force to the tires, and that's how the car is able to turn. There has to be an unbalanced force for it to accelerate. Remember, it's accelerating by changing its direction. But there is no force acting on you. And so if you're the driver, first of all, if you're the passenger, what actually happens is the door pushes against you, and you're not used to the door pushing on you because something has to make you go around the corner. So you think, oh, I'm getting pushed against the door. No. The door is pushing on you. If you're the driver, you actually exert a force through your arms and the steering wheel and you hold yourself in place. But again, you're not used to having to hold yourself in place, so you think, oh, I must be getting pushed outwards. Actually, no, your arms are pushing you inwards. Your arms through the steering wheel and a bit of friction between your seat and what you're sitting on. That also adds a little bit to it as well. Your grandfather might be the right age. If you talk to him, he might fess up. Back in the 50s and 60s, cars didn't have seat belts, and they were bench seats, not bucket seats. And if you were a hip teenage boy going out on a date with a girl, you would borrow some surfer's wax, and you would wax down the front seat so it was slippery. And then you would drive with your arm like this, and you would make a really quick right turn, and the girl would come sliding into your arm. No, that's not what happened. The girl kept going in a straight line at a steady speed, and the car moved underneath her, and she intersected the path of the driver. I'm really, really being technical. That's what's going on there. So ask your grandparents if they did that one, okay? Something we lost with bucket seats and seat belts, but we gained some safety. So, again, I need to convince you, if you're moving in a circle, which way are you moving? Tangent to the radius, not straight out from the radius. And which way are you accelerating? Everybody, toward the... Okay, put your pencils down, look up. For those of you watching on YouTube, these are two really cool videos. You want to ask me to show them to you in class. I uploaded these in my lesson and I got a takedown because, I guess one of them shows teenagers being stupid and dangerous. Sorry, YouTube. This discussion is very important because all of us, from being on amusement park rides, from going around a corner in a car, all of us think, I must be getting pushed outwards. There must be a force pushing me outwards. In fact, there's a name for this fictitious force. You may have heard people talk about centrifugal with an F there, force. That's the fictitious force that you think is pushing you outwards because you're not used to having to apply a force to stay inwards. But hopefully I've convinced you through kind of a bird's eye view that first of all, the force isn't outwards. It's in a straight line tangent to the radius. We saw them move that way. And it's actually not a force. It's inertia. It's your body's own mass wanting to keep going in a straight line at a steady speed. Thank you very much. Oh, and the vector analysis shows you that the direction is inwards. Fighter pilots, for example, if they move too fast into a loop, they can become unconscious due to a lack of blood flow to the brain, and this is sometimes attributed to centrifugal force. What's really happening here? Well, let's draw in the blood in the torso. Well, really what we should draw in to stay conscious is the blood in the brain. There's the blood. Which way is the blood traveling in that first picture? It wants to keep going in a straight line at a steady speed. We often say, oh, the blood got forced to his feet. Actually, no. His head got forced away from the blood because the blood kept going in a straight line at a steady speed. And that's why the blood can end up pooling down here, and that's why he can lose consciousness. But I gotta be fussy. It wasn't that the blood got forced away from his head. It was that his body got forced away from the blood that kept going in a straight line at a steady speed. Put your pencils down, look up.
You're ready for a big pull. We are going to do an implement, which is basically pulling right up through the inverted to the vertical to the inverted. Yep. Ready to go? I am ready. All right, take a deep breath. Okay. Flex your legs. Up we go. Oh! 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 That's the implement. You're back with me, Steve. Can you hear me?
Yes, I am. Sorry.
No problem.
So why isn't the pilot passing out? Okay. First of all, he's had training. You will never see a flabby, out-of-shape pilot. So what he's doing, could you hear him? Huh! Huh! They're doing a breathing exercise to continue to keep the blood up here. And how many of you learned when you were a kid how to make your face go red on purpose? Okay. He's doing that to force the blood to his head. I know Steve and the pilot are also probably wearing a flight suit. A flight suit has cuffs around the thighs and around the torso, and as G's increase, those cuffs inflate, preventing blood from pooling in your legs, keeping the blood in your torso and in your head. How many of you ever been to like the Abbotsford Air Show, seen the Blue Angels or the Snowbirds or anything like that? I didn't realize those guys, they can't wear flight suits because it hampers their fine motor skill too much. They're doing too close flying. They're doing it all through just core exercise and rock hard abs and breathing and forcing the blood to their head. Hashtag serious respect, because they're pulling 7 or 8 G's at times there just to make us feel impressed. Okay, so there's first one. Let's see if Steve can do it second time maybe.
Wow. I went nowhere there for a while.
Yeah, I took a little bit of a nap. That's all right. That happens on the implement quite frequently.
By the way,
Wow.
most of us would be doing the same thing.
All right, 450 knots. Looking for the obstructions, aircraft. Looking good. Here we go. Take a deep breath. Flex your legs. Here's the burners. Here we go. You're back with me. Can you hear me, Steve?
Yes.
All right, you're back with me.
Wow.
Here we go. Take a deep breath. Flex those legs.
They're tensing the legs, tensing their core, breathing, sadly, without training.
Wow. That was a long one.
It was a long one. That's why also taller fighter pilots are not wanted. Not just because it's difficult to fit them in the cockpit, but the taller you are, the more distance you've got to keep that blood flow. Shorter pilots have a way better chance of not blacking out like that. Douglas Bader was a World War II pilot. If you know your history, during World War II, there was something called the Battle of Britain. Britain's fighter pilots were holding off Germany and Italy, and it was not looking good Douglas Bader was a very good fighter pilot, but his plane crashed, and in the crash, he lost both of his legs above the knee. But otherwise, he was fine, and he still knew how to fly, and there was such a shortage of pilots. What they did is they put him in a plane, they just extended the pedals so that he could actually still pedal. And here's what he found. Because he had no legs, he could go into a dive, and he could pull up at far higher Gs than any other pilot. So he would let the German fighter pilots get behind him, and he would go into a dive. And fighter pilots being macho, and if you can do it, I can do it, the world around, the German pilot would follow him. Then Douglas would pull up. The German pilot would try and pull up. The German pilot would black out, like you saw, Steve, and crash. And it reached the point where the other German pilots, they memorized what his plane looked like, and they would warn each other, hey, don't follow that guy. We don't know what he's doing, but he can do something we can't do. It's a true story. So how do we calculate circular acceleration? Well, to be honest, the proof is a bit long. We'll pause here. On Tuesday, I'll give you the equations for circular acceleration, and we'll start to look at some basic applications. Okay? Key concept, if you're moving in a circle, which way are you accelerating? Toward the? Which way is the net force? Toward the? Which way is winner? Toward the? Which way is your velocity, though? Not toward the center. Tangent to the radius. At right angles to the radius.